And look what I've done. You see how I'm starting to build basically a deep neural network? Here I've got a linear layer that kind of munges the features together. And in fact, this might be called feature selection. What's happening is it's basically picking among the different features I have to work with and is weighting them in different weights. And I'm going to learn these weightings to learn what I actually need in this internal profile vector that represents my customers. And up here, I'll be munging together with various linear weightings the things I know about my product, both the things I learned about it and the things that I already knew about it. And I'll weight them in different scales such that these two things, when dot producted together, make a really good rating. And I guess in conclusion, thus we see that neural networks have moved into the product recommendation domain. And we can use a neural network just by approximating the dot product operation or augmenting it in various ways. We can now we can fill in this entire ratings matrix to figure out who's going to like what product. And that's huge business. Right now, industry is really interested in knowing which customer is going to respond to which coupon, right? Or which ad is going to have the biggest impression on somebody. It turns out that recommendation is going to show up all over in companies, and if you can know neural networks really well, you can build a really strong recommendation system. And there's that. Okay. What does building a recommender system have to do with dimensionality reduction or manifold learning? Okay, I'm kind of jumping all over the place, but I'm doing it on purpose because I'm trying to start tying together a lot of the things that we've learned. Actually, I'm just going to refer to this figure here. Can you see that? Come back to here. If I wanted to say, I'll start closing things I don't plan to use anymore. Okay.
You don't know what's important about the product categories. I mean, you might suspect it's something like sci-fi, but you don't know for sure. So you just try and do a learning thing to distill out whatever's important, no matter what it is. Throw all the data you have on every single movie into a model.
Yeah, pretty much. In fact, yeah, and companies will do that. They'll digest everything you have ever typed on the internet in your life, every comment you've left on a news article, anything they can somehow tie back to you. And in fact, they're probably going to take 2 hops out. Everything that somebody who they know has a relationship to you that has ever written something on the internet is going to be digested too. Because you can take all kinds of statistical information, throw it into the pot, and as long as you build a model that's going to digest it in some kind of a meaningful way, it'll learn to weight things on its own. So yeah, just by the fact that you attended University of Arkansas and that's in public records, all of a sudden things that happen at this school will be affecting your profiles at various companies for years to come. Yeah, I was going to be making a point. Oh, here it was. What is, I think my data got disassociated from my people here. There. What is Eric like? Well, in a sense, in a sparse representation, Eric is like this vector, right? Meaning, wow, this chart's getting so messy, you can't tell what I'm referring to. This green bar, all the numbers in this green bar somehow represent Eric, right? And in fact, they probably represent Eric better than this really small, dense, latent representation of him. But the advantage of this dense, small, latent representation of him is it's a low-dimensional representation of this big, high-dimensional vector, right? If we knew every movie that Eric liked, we could probably predict with pretty high accuracy whether or not he's a Democrat, whether or not he's a girl. That was kind of a funny thing to say. Whether or not, I don't know. I'm betting there's enough correlations that knowing every movie you like and every movie you hate is enough to predict a lot of things. Hopefully not everything. But if you can produce a small number, which when mapped through a common model will reconstruct all of those values, do you see that you've captured the same information into very few dimensions? Therefore, this probably still captures a lot of what Eric is like and is therefore a very meaningful profile vector for him. Okay, well, this is dimensionality reduction, is we're taking the big representation and producing a small representation that can reproduce it. And to the extent that some of these things are correlated, for example, to the extent that everybody that likes Star Wars also likes The Matrix, there's some truth to that, isn't it? And everybody that liked Titanic also liked some French chick flick movie, because they all do. Okay, that's so biased. I got to take that back. I'm sorry. I like chick flicks too. They're really great. I watch them with my wife. Okay, moving on. My point is, there's a lot of correlation between these numbers. Very often, if you know one thing they like, you also know something else they like. Therefore, finding those correlations is what enables dimensionality reduction to even be possible. And that summarization of the bigger data is an unsupervised way of learning that turns out to be very useful. If you were the NSA and you were trying to catch terrorists, wouldn't you just try to scrape all the information you possibly could off of the internet and then reduce it all to these profiles and then try to use those profiles to predict terrorist likelihoodness? And if you did, hopefully you identify the terrorist with high accuracy, then you can go knock on people's doors, or more likely, you'll investigate more closely for convicting evidence the people that are predicted to be highly likely to be terrorists. So yeah, it's a form of profiling, and it happens, but deal with it. Okay. I went through that pretty fast. Do you kind of get how we can build matrix factorization-based recommendation systems? It's okay to just say no. Yeah.
Is there like a minimum amount of the matrix that needs to be filled in in order to get that? How can you tell if you have enough data to do it?
Well, you've got the cold start problem if you've got anybody that doesn't have any ratings at all. If you've got knowledge about that person, though, then that's something, right? And it should be helpful and start working. You're certainly going to have at least one rating somewhere for every movie or every product and every corresponding customer. If you don't have at least that, then if you have some movie and it has no genre, no ratings, nothing, all you know is, I have a movie. How do you like it? Clearly, that's an impossible problem. There's nothing at all that this model can predict. So in that case, no. But if you've got one correlation between each person and each product, you can probably start teasing things out. Is that true? No, I think you have to have pairwise paths. At least two things in common. I'm uncertain about it. Here's what I know is it seems to work pretty darn well with really, really, really sparse matrices. So I think the answer is you don't have to have very much. Okay. Let's talk about another model. Which one should I do? Let's talk about generative adversarial networks. Has anybody ever heard of a GAN? Cool. In fact, before I even show you about, let's do some motivation with some photos here. Now, I think I've shown you this before. I don't think I've told you exactly how it works. So now we're going to do that today. You've seen this picture before, right, in this class? Okay. This work was done by NVIDIA. This is not my work. Half of these faces are real. Half of these faces are generated by a neural network. Figure it out. Go. Okay. Isn't that amazing, though? I mean, just the fact that half of these are not real people. Half of these people don't exist. And half of these people are genuine real people. Now, this was actually generated from, there's a data set of famous people. And they trained it on that data set. Now, what actually happened is the real people are the closest matches to the generated people in the training data. So the ones that you can see there's a lot of similarity between all the ones above and below, right? Okay, well here's the answer. The whole bottom row are genuine real people. All across the top, all fake, artificially generated people. And you can see how different they are from the people below them. That difference is the imagination of the machine. This is it just decided to pick a random person. Now, let me bring up so you can imagine that there's some type of latent input space such that if you have a position in this space, and it doesn't have to be two-dimensional, it could be 20-dimensional, but every point in that space could be fed as the input into some model such that this model would then output a image. Wow, 3 boxes that all mean different things. Let me label some stuff. This is a model. This is a latent space. This is a picture. And just to make that one clear, there. Clearly that one's a picture. To make the model clear, let's draw some neurons in there and connect them with lines. Oops. And what's a latent space? This is a n-dimensional space of all possible latent vectors that could be used to represent a person, right? Now imagine in assignment 6, we trained on those crane images and we backpropped across our network and we also updated these inputs such that we eventually got a pretty decent picture on the output end, right? Okay, well, suppose you then took that latent internal representation and moved it a little bit. What would you get? Basically, as you move this latent input, you could imagine this picture morphing, right? Such that every spot in this input space represents a corresponding image in that output space. Well, your training data has a bunch of pictures to start with, but you end up with a bunch of corresponding latent representations. As in, these are low-dimensional reductions of the corresponding high-dimensional pictures. And the way that we generate a new image that we've never seen before is we pick a spot in here that we feel like is on this manifold. See how there's kind of a manifold of interesting points and how there's no points over here? Well, if we pick a spot over here and we generate the image, we're going to see garbly garbage, right? But if I pick a point, say right here, it's on the manifold of good-looking images, and I run that through my model, I'm probably going to get something that looks like a person because this thing has learned to recognize people. And that's the principle behind which this whole thing operates, is all of these faces are on the manifold of what the neural network believes are good-looking faces. And look at them. I mean, they're just very realistic. This person has weird hair stretchy things that don't happen to real humans. So we were able to say, okay, that one's fake. Real secret is look behind them. See this, these funny backgrounds that are synthesized, and these ones have sharp letters here. The neural network actually synthesized fake advertisement-like backgrounds because those tend to occur with the celebrity pictures. And so you can't quite tell, but just by virtue of this doesn't say anything real or doesn't look like a logo, you can tell that one's fake. And this one's real because it has real letters right there.
You can assume like the neural network isn't going to produce any frowning people.
Yeah, it was trained on smiling, happy people, so of course it's going to produce smiling, happy people.
So like the second person and the third person.
Yeah, that's kind of a fake smile, and that person too. I don't know. Of course, that guy's kind of not super beaming.
But then you can tell that the guy below him is real because he's not symmetrical. And I'd assume that the neural networks would mostly make symmetrical people.
Oh, that's a good point. You'd assume it's averaged out to the point where it always generates symmetry. Oh, whoops, I was looking at my screen over here and you were looking at that screen. Sorry. Yeah, in fact, there's this really cool, there's a YouTube video of this. If you look up NVIDIA GAN faces, there's a really cool video where what they do is they actually take that latent point and they wander around at a continuous rate, and you get to see the faces morph between movie stars while staying human looking like. And it's really cool. So if you have some time, go look up that picture. Unfortunately, I'm out of time today, but hey, generative adversarial networks are another thing that I haven't yet explained and will hopefully explain to you next time.
Wasn't there a whole app that was like doing this and people got mad at it?
Yeah, people are starting to get scared of, they can now take neural nets and you can stick random heads on other people's porn pictures, and you can, it's starting to get scary how effectively it integrates it to the point that humans can't tell anymore. And there's a bunch of, I don't know, we're on the brink of, we're going to start having new laws as to what you can do with neural networks in consequence of this.